Okay, maybe I'll start. Okay, so let's start. Okay, thanks for coming. So I'm going to be telling you today about some recent progress on the sunflower lemma. So let me start first with just telling you what the lemma is. So we're in the situation where we have a family of sets, S1, S2 to SL. And all of these sets live in the universe of n elements. Okay? And they're all distinct and of size k. What is a sunflower in this collection of sets? It's p sets that look like this. Okay, so p sets with the property that, so here I'll just draw a sunflower with 3 petals. So a sunflower is just a collection of 3 sets where all their pairwise intersections are exactly the same. Okay, so in this case, it's a sunflower with 3 petals. Whenever you take the intersection of any 2 sets, you get exactly the same set, no matter which 2 sets you pick. And the question we're interested in asking today, and this is an old question, is how large can L be? How many sets can you have in your family of sets before you're forced to contain a sunflower with p petals? Okay, so that's the main question. So how large can L be before there must be a sunflower with p petals in these L sets? Okay. So that's the question I'm going to study. It's a really fundamental question. It was first asked by Erdős and Rado, who gave an answer for this question. What they proved is that, and they did this in 1960, that if L is bigger, if the number of sets in your family is bigger than p minus 1 to the power k times k factorial, then you get a sunflower with p petals. Okay. That's what they showed. And besides being a beautiful and fundamental question, this theorem, or this lemma, as I think they called it, has many, many applications, both in computer science and in mathematics. In computer science, perhaps the most famous application is it was used as a fundamental, in a very important step in Rasbar's proof of lower bounds for monotone circuits computing the Clique function. That's one place where it was used. But since then, it's been used in many, many places in computer science, and also many places in mathematics. Shiva and I have a paper from last year where we used the sunflower lemma, this lemma, or something like it, to show lower bounds against for data structures that compute statistics of sets. Okay, so it's a really basic lemma. It has many applications, and for a long time it was open. It's still open. You know, what's the correct number to have here? Okay, another way to ask it is, what's the smallest family of sets where you can avoid sunflowers with p petals? So there are other bounds that depend on n. I talked about one of those bounds last week when we were in theory lunch. But here we're interested in bounds that are independent of n. Okay? And we'll show some. So this is what they showed. And what I want to tell you about is some very recent progress on this bound. So just a few weeks ago, there was a result of Alves, Lovett, Wu, and Zhang, who showed the same statement but with a much better bound. They showed that if L is just bigger than a quantity that looks like log k to the power k times p log k power order 1. Then again, you get a sunflower. Okay. So one way to think about the theorem of Erudish-Narado is this looks like p minus 1 to the k times k to the k. Okay. And basically, what they did in this bound is replace the k to the k with log k to the k. That's one way to think about what happened here. So this looks like p to the k times k to the k, and this is like log k to the k times essentially, oh, sorry, here, this should be k. Now it makes sense. Okay, so this looks like p to the k times k to the k, and this is log k to the k times essentially p to the k. Okay. And this is really a phenomenal result because this problem has been open for almost 60 years. Lots of people have tried to work on it. All the methods you try seem to fail prior to this work. So it's a very exciting result. And when I heard about this paper, Paul told me about it. I immediately felt like I had to understand what was going on here. So I read it, and after I read it, I managed to simplify the proof. So that's what I'm going to show you today. So the theorem that I'm going to prove to you is based on the same ideas as in this paper, but I'll show you that if L is bigger than, so I'll show you that there's some constant alpha, and as long as L is bigger than alpha p log pk log of p log pk to the k, you get a sunflower. Okay, so that's the bound I'm going to show you. And it's still open what the correct bound is, but this seems like these kinds of bounds seem to be really somehow limited by the kinds of proof we're going to use to prove them. So I would imagine that to beat this bound, you need to have a different idea or a better idea. I should say that there's a counterexample that shows that there is a family. So there is a family of p minus 1 to the power k sets and no sunflower. It's not hard to see. So the best you can hope to prove here is something that's like p minus 1 to the k. Okay, and this is really what Erudish-Narado I think believed to be the truth. Okay, so really it should be possible, or as far as we know, it should be possible to completely get rid of all the terms here and just have something that looks like order p to the power k. Okay, and that's the main open question that's still left open. So that's my plan today, is just to show you this proof. Are there any questions about the setup of the problem or the definitions we're talking about?
So how do these bounds compare?
How do these bounds compare? They're roughly the same. One thing is that here it's clear that the power of p is really k, and here it's all of these log terms. They basically this inner expression is basically p log k. It's there's some log p terms too, but it might look that this is strictly stronger at first because this k is the power here is really k and not order k. So the dependence on p is a little bit better. But it turns out that actually in their proof, this constant here can be brought very close to 1. So, and their proof is very complicated, so it's hard to actually understand what the constant is. Yeah, I'm not exactly sure how they compare. Any other questions? Comments? All right. So the plan is for me to show you this proof. Now, really, if I just tried to show you the proof step by step, I think I would finish in 15 minutes. And it would be a proof, but it would be very confusing because it's a very confusing counterintuitive proof. So what I'm going to try and do is take a longer path with several guesses to the proof, which I hope will provide more intuition for the final proof, if it works out. So that's what I'm going to do. So let me start first by telling you, actually we'll see, let's start by just doing Aradosh and Rado's original proof, okay, of the weaker bound. So here's the idea. So suppose, so let's now prove this bound. The idea is try to just find, so we're looking for a sunflower with p petals. So just try to find a sunflower with the greedy algorithm. Just try to find actually p disjoint sets. So you have a collection of sets. Find one set. Then if there's another set in the family that's disjoint from that set, find that set. And then now you have two sets. You want another set that's disjoint from all those sets you have so far. Keep going in this way, right? In this way, you will either find p disjoint sets. So either, okay, so I'm starting the assumption that you have so many sets. L is bigger than p minus 1 to the k times k factorial. Either there are p disjoint sets, okay, or the second case is that at some point your algorithm fails, right? So at some point you found some number of disjoint sets, and then you can no longer find any other disjoint set. And this is because every set in the family now intersects one of the, at most, p minus 1 sets that you have so far. That's why you're unable to find a new disjoint set. Okay. So at this point, you must have found a set T whose size is at most p minus 1 times k. Okay, this is the union of all the sets you found so far that were disjoint, such that every set in the family intersects T. In S1 through SL intersects T. But this means if every set in the family intersects this one set, by averaging it means that there's one element of T that is contained in p minus 1 to the k times k factorial divided by p minus 1 k sets. So there must be this many sets that share a common element. Okay. Just by averaging, I have here that many elements, and each one, every one of these sets hits one of these elements. So by averaging, there must be one of these elements that's contained in that many sets.
More than that.
More than that many sets, yeah. And now I can just, so if you see this formula set up exactly, so this happens. This is equal to p minus 1 to the power k minus 1 times k minus 1 factorial. Okay, so now I can complete the proof just by induction, because now I have this one element that's in this many sets. Okay, if I take that element out and I delete it from all of these sets, I get sets of size k minus 1, and this many sets of size k minus 1. So by induction, these k minus 1 size sets will have a sunflower with p petals. And if I take that sunflower and put this common element back in the middle, I'll get a sunflower in the original family. Okay, so you continue by induction, and you find a sunflower. Okay. Does everybody understand that proof? Okay, so the key step in this argument was somehow there are two cases. Either this greedy algorithm works, it finds p disjoint sets, or something else happens, you find one element that's in many sets. Okay, the sets must sort of overlap quite a bit. And what these guys did, what Alvej, Lovett, Wu, and Zhang did is just generalize this dichotomy a little bit. Okay, so let me show you the structure of the high-level structure of the proof. So the first thing we'll do is let's actually, so let me call, throughout this talk, I'll refer to this quantity as R. Okay, so this quantity inside the bracket is R. So this is R to the K. So let me give you a definition. So let's say that a family of sets, the sets are R well spread if whenever you take set Z, the number of sets containing Z is small. Okay, is at most R to the power of K minus the size of Z. Okay. So the family is well spread. If whenever you take a set Z, then there are not too many sets that contain, that all simultaneously contain Z. Okay. And here's a lemma that we'll prove. This is the main technical lemma. If L is bigger than R to the K, okay, that's the assumption, and the sets are R well spread, then they must contain actually p disjoint sets. So that's the key technical lemma. And once you have this lemma, you can just plug this lemma into this proof, and it's basically going to work out. So let's try and change the proof now using this stronger lemma. This lemma is basically the analog of the greedy algorithm here. Okay. So let me let's change this proof now, assuming this lemma, and prove the main theorem we want. So there are two cases. The first case is that the family of sets that we have is R well spread. And in this case, we're done, because the lemma promises that there are p disjoint sets. Okay. So we get sunflower, done. And if this is not the case, then what does it mean that the family is not R well spread? It means there's a set Z there's some set Z contained in R to the power K minus the size of Z sets of family. So what should you do? You do exactly, you just do induction, right? So instead of one element, now we found these elements which belong to the set Z. Take them out and consider these R to the K minus Z. It's actually greater than. Take all of these sets that contain Z. There's more than R to the K minus Z of them. So by induction, you get a family of sets of size K minus the size of Z. And this family has R to the K minus Z, more than R to the K minus Z sets, so they contain a sunflower. By putting Z back into the core of the sunflower, you obtain a sunflower on the original sets of size k. Okay. Does that make sense to everyone? Okay, so this is the key lemma. This is the thing we need to understand. It's the key technical step of the proof. We need to understand how do these well-spread families of sets behave. And specifically, we want to show that any well-spread family contains p disjoint sets. So let me start explaining how to reason about this.
So before you do, there's something slightly confusing. I mean, this makes sense, but you've described R kind of independent of K, and in the examples are kind of dependent on K. Future K is now K prime.
Yeah, k gets smaller, but the r only increases with k, so it only helps. So what happens, you have r to the k minus z, the k is smaller, but the r that you're going to use in the next step is actually smaller than the r you have. Okay, so it's true that it's a little misleading, but it only works in the direction that you want. Yeah. Any other questions or comments? All right, so the key thing is to try to understand what does it mean for a family of sets to be well spread, and how can we leverage this to say that there should be sets that are disjoint. Actually, even understanding, forget about finding p sets that are disjoint. As far as I can understand, the hard part is just showing that there are two sets that are disjoint. Even this is challenging. Okay, so so let me try and give some intuition, at least my intuition, for why this should be the case and how the proof goes. So think about, intuitively, because the sets are well spread, they can't sort of cluster into a small part of the universe too much. Right? If a ton of sets cluster in a small part of the universe, they'll share some elements quite a bit. Okay? So that shouldn't happen. And so one intuition might be that if you take the universe, so here are the elements of the universe, and just permute the elements of the universe randomly. Okay? So rearrange there are n elements in the universe, rearrange them randomly. And let's break up the universe into p pieces. So let's look at n over p elements here, and then n over p elements here, and so on. What I would like to hope is that some set in the family, I have many sets here, and they're also well spread, that some set of the family will fall completely in the first part, another set of the family will fall completely here, and the other set will fall completely here, and so on. If this happens, when I apply a random permutation to the universe, then I have this property that p of the sets really split into these p different parts, then these p sets have to be disjoint. Right? So I'm done. So one way to think about doing this, in fact, this is what we'll do. So we'll actually employ a random argument where we'll think about taking a random partition of the universe into p disjoint sets. And we'll argue that with positive probability, each part of the partition will contain one of the sets of the universe. Okay, so this will prove that there are p disjoint sets. So our eventual goal is to show, in fact, what we'll show is something even stronger. So we'll show that if W is a random subset of the universe of size n over p, then what I want to show is that the probability that there's some set of the family that's contained in W is bigger than 1 minus 1 over p. Okay. So with high probability, if you pick W to be n over p fraction of the universe, one set of the family will land completely inside W. And if that happens, if I can show this bound, we're done. Because by the union bound, this first part of the universe is a random set of size n over p. So with high probability, it'll contain one of these sets. The second part is also a random set that contains a set with probability 1 minus 1 over p. So by the union bound, with positive probability, each one of these sets will contain a set from the universe, and then that'll give you p disjoint sets. Okay, so this statement is enough to prove the lemma. Okay. All right. So why should this statement hold? So to start reasoning about it, maybe one way to think about it is we're looking here for the condition that some set of the family is completely contained in W. Maybe a weaker thing that you could think of to try and make progress is just hope that, say, for some set, most of its elements are in W. You can measure for each set W, what is the extent to which it swallows up some set completely. Maybe it doesn't swallow a set up completely, but if it swallows 90% up, maybe that's easier to understand. Okay, and that's actually, I think, a key step in the intuition for how we'll get to the eventual proof. Okay, so eventually we want to prove this statement, and we will prove it. But it's easier to understand the simpler statement that the probability that W swallows up 90% of some set is actually very high. Okay, so I'm going to try and prove that statement first, because the proof of that statement is much easier, and then we'll get to proving this statement. Okay, so let's now imagine. Let's try and understand. So what I want to do is understand. So actually, I'll try and analyze this probability. The probability. So maybe I'll analyze an even easier thing. So let's analyze. Let's imagine that W is a uniformly random set. Okay, meaning not of size n over p, but just a uniformly random set. And I want you to understand what is the probability that there exists some j in the family such that Sj minus W is of size bigger smaller, let's say, smaller than smaller than some parameter t. Okay. Let's try and understand this probability. Okay. So here's an argument. You can think about this for a while, and here's an argument that puts a bound on this probability. So let's look at all the W for which this does not happen. Okay. Meaning that, so what are the bad W's that we're worried about? So you take W, and whenever you take a set S from the family, a lot of it sticks out. Okay, so you have T elements sticking out here. Whenever you take a set S from the family. So these are this is the kind of thing that we want to avoid. Okay?
Bigger than T.
Bigger than T, sure. So here's one way to count the number of such W. So consider the following. So we're going to use an encoding argument. Okay, so and what we'll do is we'll encode we'll count actually the number of. We'll count the number of pairs the number of bad W, the number of tuples which have a bad W and a set S from the family. Okay. This is from the family.
So S is a one Which S is it?
So S is one of the sets in the family.
Oh,
So I
okay.
want to show that the number of bad W's is small. This is what I want to do. Right? I want to argue that if you pick a random W, the probability that this event happens is small.
Is this W bad for that S or for all S's?
For all S's.
Okay.
Okay, for all S's. And what I'm going to do, the way I'm going to do this is I'm going to count the number of pairs where I have a bad W and any set S from the family. Okay? And if I can count that, then I'll get a count of the number of bad W's. Okay? But the way I'll count this is, first, let's count the number of options for W union S. Okay? This is just some set in the whole universe. Okay? So there are at most 2 to the n choices for W union S. And the next thing I'll count, so the key point is that once you know W union S, so suppose you have here W and here S. I don't know what S is, I don't know what W is. But one thing you can find is you can find some set, some arbitrary set, Sj in the family that's contained in this union. Yeah.
I'm confused about W union S. What exactly does S? Is it a union also with the families or?
No, S is a single set from S1 through SL.
But then I have fewer than 2 to the n choices.
In the worst case, you have I just want an upper bound. So this is some set in the whole universe. So at most 2 to the n such sets.
So this set must contain some Sj by definition.
It must, yes. In particular, it contains S.
Who says?
S is the set we're encoding. Okay, so I'm going to somehow count the number of pairs here. Okay, I'm going to start by counting the number of choices for the value of W union S. There's 2 to the n of them. Now, once you know W union S, it doesn't mean you've determined S and W. Okay, but we're going to now count the number of options for S and W given this choice. So once you know W union S, you can determine at least one set, if you just find the first set in the family that falls inside W union S. There has to be one set because S itself satisfies this definition. So let's say this set is Sj. Sj may not be equal to S. Okay? But the key point here, okay, so now that I've determined Sj, what we'll do is we'll look at the number of choices for Sj intersect S. Okay. Which is this region. The number of choices for this intersection is at most 2 to the k. Right? So Sj is determined by W union S. And once you know Sj, there are 2 to the k possible choices for Sj intersect S because there's some subset of Sj. So we'll encode that, or we'll just count the number of choices there.
So J is determined by the first
element.
J is determined by W union S. Yeah.
Okay.
And now here's the key place where the argument is going to use the fact that the family is well spread. Okay. The point is, the point is at this point we've determined a large subset of S. And how big must this subset be? It contains this set, which is Sj minus W. And here already there are at least T elements.
Strictly bigger than T.
Oh, strictly bigger, doesn't matter. Okay, so we found a huge subset of S. And the number of sets S that contain this large set, there's very few of them because the family is well spread. Okay, so now the number of choices for S is at most r to the k minus t.
So the order in which you choose these sets is bizarre. So initially S looked like it was fixed. And now you're saying that there are a fixed number of choices, but you already fixed S.
No, I want to count. So I'm trying to count the total number of options for these combinations.
Where S is a subset of the family.
No, S is one set in the family. So S is equal to either S1 or S2 or S3.
When you say one subset, it's not a fixed one, but it's any choice, right?
We're taking all possible pairs here, every bad W and every S from the family, and we're counting the number of those pairs. That's what we're doing. Okay, we're counting the number of pairs. And the way I'm counting that is I'm counting the number of options for W union S. Then given a fixed value of W union S, counting the number of options for Sj union intersect S, and so on. So overall, I'm getting an upper bound on the total number of pairs of the type W, comma S. Okay, so once I know Sj intersect S, I've determined a subset of S, and this restricts the number of options for S. You know, just knowing this value, it doesn't determine S. But now there can be only r to the k minus t such choices for S. Because every feasible choice for S must contain this set. And it's a large set. Okay, and then once I know S, I can specify W intersect S. Okay, this is 2 to the k choices. And now, so we've encoded, so sort of we at this point we know W union S and W intersect S, which means you know both W and S. Okay, so what you get is that if you count up what's happened here, we get that the number of pairs WS, it's at most 2 to the n times 2 to the 2k r to the k minus t. And this means because the number of options for S, so this is the number of bad W times r to the k, right? Because the number of choices for S from the family is r to the k. So that's at most 2 to the n, 2 to the 2k, r to the k minus t, which means that the number of bad W is at most 2 to the n times 2 to the 2k divided by r to the t. Okay, so in other words, this number here is a fraction of bad W's. It's a fraction of bad W's. So if you set r to be some large constant, then, for example, if t is like even k over 100, what you get here is that with high probability, except with exponentially small probability in k, there will be some set that's 99% of it is swallowed up by W. Okay. And this is sort of the key idea of the proof. So if anyone has any questions, now would be a good time to ask. Maybe I'll say one more thing. One more way to think about what's happening in this proof. So, suppose you pick a completely random set W from the universe. Then for any fixed S from the family, you will expect W to intersect that S in half the elements, right? So you would expect W to include roughly k over 2 of the elements, and exclude roughly k over 2 of the elements. And we have concentration bounds that say that with extremely high probability that will happen, right? But what we're proving here is that actually, with really good probability, even though for most sets this will be true, you will take up half the elements, there will be one set for which W will take up 99% of the elements. So in some sense, this is the form of an anti-concentration bound. So we are saying that there are going to be sets where the fraction that are swallowed up by W is much closer to 99%. Okay.
So random question.
Yeah.
Since you spoke once about anti-concentration, does this approach also translate to?
No, it doesn't.
No.
It's a different set. Okay, so from this point on, I think this is the intuition that's common to both the original proof and then the
You can use the blackboard behind.
oh, yeah.
Slide that one to the left.
This is the approach that's common to both proofs. But what I from this point on, what the original authors, the people who proved this result, did is they tried to carry out the proof now by induction. So you start with if you think about what's going on here, you start with a family of sets S, and kind of you'll expect that there will always be the set Sj. What this argument really shows is that there's always going to be the set, with high probability there will be the set Sj where Sj is swallowed up quite a bit by W. Okay, so if you pick W at random, then what's going to happen is W may not completely cover S, but it is going to cover this other set Sj that's somehow related to S. Okay, so the strategy that they tried to carry out is to do induction on the family of sets. So initially you start with a whole bunch of sets of type S. You pick some set W, and after you pick this W, you replace every set S in your family with this set. So W already covered up this part of Sj, and it has some part that's left over. So you then try to erase S from the family and replace it with this part of Sj that's left over, and repeat the argument. Okay, try to pick a new set W prime, which you will take the union with W, and add it and try to cover some set of the family this way. Okay, so that argument turns out to be quite complicated. And what the proof, the way I want to show it, also uses the same picture, but now I'm going to look at a different quantity. So let's a different strategy from this point on. Let's so this picture maybe inspires the following definition. So given an arbitrary set W and S from the family, let's define chi SW to be this set. It's going to be a set of the Sj minus W, where Sj is chosen exactly so this area is minimized. Okay. So Sj is some set of the family chosen to satisfy Sj should be contained in Sj union W, and the size of Sj minus W is minimized. Okay, so it's really in this picture, it's this set, this shaded set. And the lemma that I'm going to prove, maybe I'll write it here. Actually, I'll write it here. So the main lemma is that if W is a uniformly random set of size n over p, the expected value of the size of chi SW is small. Okay. This is what I'm going to prove. And that actually implies that bound. So maybe a couple of observations about chi SW. The first thing is that if W includes some set of the family, then chi SW becomes empty for every S. Okay, because as soon as there's some set Sj that's completely contained in W, then that Sj is a candidate here. And Sj minus W is empty. Okay? So when a set of the family is contained in W, then chi SW vanishes for every S in the family. Okay?
Can you have the opposite, that no Sj satisfies the condition that is a subset of S union W?
No, because S is always going to be a set of the family. So S itself satisfies this condition. So we'll always apply this with S, a set from the family. Okay, so what happens in this definition is when this quantity becomes empty, it becomes empty for all S. And when it's non-empty, it's also non-empty for all S. Because as soon as it vanishes for one set, it means really that that set is contained in W, and then it vanishes everywhere. Okay? And then you can see just by Markov's inequality that if you can show this, if the expected value of this thing is at most 1 over p, it means that the probability that that quantity is at least 1, that's exactly this probability. And that probability is at most 1 minus 1 over p. Okay, so this bound just implies that bound in the probability. Because as soon as this quantity becomes 1, as soon as some set is, every set is not covered by, there's no set that's covered by W, then this quantity will be 1. And the probability of that event can be at most 1 over p. Okay. All right. So now I'm going to show you how to bound this. And the way I'm going to bound this is, again, using a generalization of what's happening here. Okay, so we'll just follow this scheme of doing an encoding argument. But it won't be as straightforward because here what's happening is basically counting. And to make the proof work, I'm actually going to have to say something about encodings and not just counting. Okay, so to give you some intuition, so what actually the way we'll prove this is by induction. So really, the thing we'll prove. We'll actually prove that for m, for some parameter m that's equal to 1 to some integer, if you pick W of size m times roughly n over, actually, to make the parameters work out today, I'm going to make the calculations a little easier by setting, let's set R to be this quantity, p log pk squared, maybe 100. Okay. And then here's the statement that I'll actually prove. So if you pick a uniformly random set of size m times n over squared r, then I'll show that the expected size of this quantity is bounded by k times 2 to the minus n. Okay. And once you can prove this, this implies the old bound, because if you set m to be equal to log of pk, then you'll see that this thing becomes something that's less than n over p by the choice of parameters. Okay, something that's less than n over p. And this thing becomes something that's less than 1 over p. Because 2 to the minus m is like 1 over pk.
Is it p squared there in the top part? Or 100 p squared log squared pk?
No, I think it's correct. So here I only have log pk. Oh, I see. There's a square root, yeah. Okay, yeah, you're right. Yeah, okay, good. Okay, so the way I'm going to prove this is by induction. and now I'll outline how the encoding works. And it really just parallels this encoding over here. So we'll imagine that W is equal to the union of two sets, U union V, where U and V are disjoint. And the size of U, it's this quantity little u, which is m minus 1 times n over squared r. And the size of V is, call it little v, which is equal to n over squared r. Okay. So the way I'm picking W is I first sample this set U, which has m minus 1 steps of the induction, and then the last step of the induction. And then what I'm trying to prove here is just that the expected value of the size of chi SU, chi SW, is bounded by the expected value of the size of chi SU divided by 2. Okay? Because by induction, U is a uniformly random set of size. It's a case where m is equal to m minus 1. And then now we want to say that when you add this v, the expected size is dropped by a factor of 2. Okay? So this proves the statement of the lemma. Okay. So I won't have time to verify all the details, but I'll maybe just tell you how the proof works. It just really follows this statement. What we're going to do is try to encode the number of pairs. So we'll fix a set U. And we'll actually prove this inequality for every U. So we'll fix one set U, and then we'll try to encode the number of pairs V comma S, where V is a set from the universe of size n over squared r, and S is some set from the family. And the things we'll encode are, we'll first encode the size of chi SU. Basically, I'm going to encode everything everywhere here. Instead of S, I'm going to have chi SU. And otherwise, the encoding is the same. So encode this, encode the size of, encode W union chi SU. And then we'll find the first J such that chi Sj U is contained in W union chi SU. Exactly like that. And we'll encode the size of chi Sj U intersect chi SU. And then we'll encode S. And the key thing that's going to happen is that this set, its size will be large. It'll be bigger than the size of chi SW. Okay. The intuition is exactly the same as what's happening here. So intersection Sj intersect S here was large. It was larger than this set. And the role of this set is played by chi SW in this encoding. So you'll be able to argue that this intersection will be large. So that'll give you a cheap way to encode S, and then you can cheaply encode S intersect W. Okay. So you have some encoding here of this space. The reason things are a little more complicated is here we just did a counting argument. Here what happens is I can't just count the number of pairs V comma S, but it turns out what I can do is talk about the length in binary of this encoding. And what you can show is that if you have a set of size t, then to encode it using binary strings, you need on average at least log t bits. Okay, this is a converse to Shannon's noiseless coding theorem. if you apply that fact to this encoding, it ends up, the length of these, every term in this encoding has length that depends on either chi-SU or chi-SW. This takes chi-SU bits. This takes, it turns out, the size of W plus chi-SU bits. When you figure out the length of this encoding and then apply the fact that the number of bits you need must be at least log of the number of choices of VS here, you get back exactly this inequality. So I guess I don't have time to do the details, but I hope you got some intuition about how it works. I'll stop here. Thanks.
So is the issue on the size, because before you knew W union S exactly, now you've got, so S was a fixed size that you knew, is that the reason why you need the codes, because these chi's can vary in length?
Yeah, so what happens is, here we had these numbers K, but if you try to do that over there, those numbers depend on the size of the sets that you're working with and how much they drop. So that's part of the problem. That's why it's not so easy to just do a straightforward counting argument. Any other questions or comments? Yeah.
So you said that to improve this result, you take like new techniques. Is it because the lemma of the well spread sets is tight, or?
No, that one is not tight, but this one is. So this kind of statement, that this happens with high probability, or the probabilistic statement, that with high probability when you pick a W, there will be a set containing W. That's known to be not true if you use better parameters for R.
I see.
Okay, so any proof that improves this, you somehow have to avoid talking about uniformly random sets and hoping that they will contain some set of the family.
I see.
For that statement, everything you see here is type. But one thing I was hopeful for, which is related to why I talked about polynomials on Friday, is that maybe you can take some of the definitions here and somehow combine them with ideas, say using polynomials or completely different ideas, not a probabilistic statement, and then you would avoid the counterexample and prove the bond.